So the purpose of this session is to really, the other brainstorming sessions that are happening right now are around very specific energy technology topics. What we're doing here in this session is really trying to give you a peek under the hood of some big new ideas that we're incubating at kind of the earliest stages. And my name is David Danielson. I am a program director at ARPA-E and also the nominee to be the next Assistant Secretary of Energy Efficiency and Renewable Energy. And to my right are 4 of ARPA-E's fellows. So the ARPA-E Fellows Program, what it does is we reach out and we try to find some of the best and brightest recently minted PhD students, engineers and scientists, to come in and serve as an incubator where we can bounce around and develop completely game-changing new ideas. And some subset of these ideas will likely end up being workshops that we'll run, and then possibly a subset of those will end up being an actual ARPA-E program. The way we're going to run this panel is that each of the fellows is going to give a 6-minute quick pitch on an idea that they've been incubating. And after that, we're going to open it up to the audience for questions and comments about these specific programs. And then towards the end of the panel, really like to encourage you to stand up and tell us what are some new areas that you think ARPA-E should be working in where we haven't worked before. Last panel didn't get as many of those ideas as we wanted, so I really encourage you to stand up and be heard. This is a great opportunity for you. With that, I'm going to pass it, a couple logistical details. We have cards, you should have note cards on your chairs where you can write down questions or comments and then send them into the middle of the aisles. Those will be brought up to me, and I'll be moderating the session. In addition to that, we'll be taking questions and comments from the microphones. And with that, I'm going to pass it over to the fellows.
Thank you, Dave. My name is Phil Rochelle. I'm a postdoctoral researcher working at ARPA-E. I have a PhD in physics from Harvard University. I did my doctoral research at CERN, the European Center for Nuclear Research. After my PhD, I worked as an energy analyst at Lux Research in New York City, and then again as an energy analyst for an energy nonprofit here in DC. This session I'll be speaking about ideas surrounding the forecasting or prediction of power output from variable renewable energy generation sources such as wind and solar power. So, as we all know, the wind doesn't blow all the time, the sun doesn't shine all the time. This graph is from the National Renewable Energy Laboratory from one of their large data sets, and in blue you see what the actual wind production from this site was. And this particular data is from the worst forecasted day of the year. So what you see in black is what the prediction of what the wind was going to be a day ahead. And so you can see for many hours over several days there's a disparity of over 100 megawatts in terms of what people thought that the wind output would be compared to what it actually was. And then the prediction does get better as you get closer to the actual time of production, but sometimes not all that much. So in red, what you see is the 4-hour ahead forecast, which means that even closer to the time of production, there was still a horribly bad forecast. Now, in terms of what typical errors in the state-of-the-art forecasting are, there's typically more error for a day-ahead forecast than an hour-ahead forecast. And there's more error for a single site than there is for forecasting over an entire region. And that's because their errors tend to cancel out and weather phenomena are kind of easier to predict. So as we can see, the average forecast errors range from about 3 to 30%. But the bigger problem are actually the outliers, which can be much bigger. So it should be noted that this data is from 2009 and the state of the art is constantly improving. But the key point, nevertheless, is the fact that bad forecasting results in a number of costs to the system. So first, there's the requirement of additional balancing reserves. If the wind or solar output isn't as high as you thought, you have to be more conservative and allocate enough balancing resources like a natural gas plant or the equivalent, which can kind of pick up the slack when the wind isn't what you thought it would be. Second, another cost to the system is there's often the need to actually cut back or curtail on the wind and solar production. And the reason for this is that if the wind is higher than what you thought it was, the other assets on the grid, such as an old coal, nuclear, or natural gas plant, actually can't ramp down fast enough to allow the wind to ramp up. So then you literally throw away electricity, which is of course a huge wasted resource. And lastly, if there's a big forecasting error, the difference in power production can be such that it overwhelms the system's capability to cope through ancillary services and balancing reserves. And there you can get into a reliability compromising event such as a contingency or an outage. This is the kind of thing that we've been seeing in Texas and Europe. In terms of what the economic value of a better forecast would be, there's a number of studies. This is one of them from the National Renewable Energy Lab and General Electric. And basically what they say is that if you could get a 10% or a 20% forecasting improvement, and they describe what that means, based on what the wind penetration level you have is, you can have savings to the system which are on the order of hundreds of millions, even going up to $1 billion. But a larger point, which isn't really spelled out here because you can't quantify it, is the fact that grid operators just will not allow a certain amount of renewable energy penetration if you can't predict with some reasonable accuracy what the power production is going to be. So in terms of setting a goal, what we want to put out to the community is kind of a grand challenge. NREL is talking about a 20% improvement in forecasting. So what if we put out a challenge to have a really radical increase in forecast accuracy so that you could have something like a greater than 40% improvement in state-of-the-art forecasting techniques for wind and solar power? Now, when we think about how we can tackle this problem, we have kind of divided this into a hardware side and a software side. On the hardware side, we're interested in better data sensing techniques for meteorological data such as wind speed, direction, pressure, temperature, irradiance, and so forth. Now, right now, the sensing is limited, so we either want to lower the cost of sensors or we want to have it so that a single sensor can kind of detect over a large area. Preferably, we want to have some combination of both. On the software side, we want to look into new ways of kind of aggregating all that data and processing it efficiently, and then using it in the proper predictive models to get a better forecast. We also want to package the results, which are probably going to contain things like probability distribution functions, in a way that's useful to grid operators. For the state-of-the-art, on the hardware side for wind, the techniques which are currently used are things like cup anemometers, which spin depending on what the wind speed is. You have radar, which is used much like in aviation. And then you have another thing called SODAR, which is sound detection and ranging. And this works quite a bit like radar, except it uses a pressure wave instead of an electromagnetic wave. Now, thankfully, I understand that these are not in the audible frequencies, but I'm still not sure if I want to bring my dog near one of these things. We have to be on the lookout for radical improvements in all of these things in either accuracy or cost. But personally, I'm not exactly sure how we can jazz up the cup anemometer. But if there are any suggestions on that, please let me know. But another technique which is starting to get some traction is called LIDAR. So this stands for light detection and ranging. And what this does is it uses pulsed laser light. And so when you use pulsed laser light, you can get information about both the distance and the velocity of the wind. And the way that that works is that the distance is by a time of flight measurement from when the light bounces off something and then comes back to the detector. And then the speed is actually because when you scatter off of something, there's going to be a frequency shift in the light depending on what the velocity of the thing you're scattering off of is. This is called the Doppler shift. So by looking at both the time of flight and the frequency shift, you can tell both range and velocity of wind, potentially over a large area. So right now, these things are kind of used as stationary resources where you kind of put them down and you use it to characterize what the wind resource over the course of a year is to help you decide whether or not you should build a wind site there. And then these very expensive boxes are moved to the next wind site to decide if, that should be another place for the wind site. There are some instances of range LIDAR being stationary for a long time used in other applications. So there's some applications where LIDAR is being used to decide the optimal way to position the wind turbine depending on how the wind is coming in at a particular time. So a natural question to ask is, if we could radically bring down the cost of LIDAR and also extend the range so it can go to kilometers or even tens of kilometers, could we then radically increase the amount of data that we can feed into forecasting models to do better forecasting? On the solar side, there are instruments called total sky imagers, which take kind of wide aspect ratio pictures of the entire sky. They then feed this into a data processing unit that can then try to predict cloud formation and things like that. But another potential resource which we have are photovoltaic cells themselves. When you think about it, a PV cell is really a really fast time scale irradiance sensor. Right now, this time sensitivity is lost because we just dump this energy on the grid. But what if we could log this and communicate it back? Then we could have a network of kind of local irradiance sensors. For rooftop PV, you could have this across an entire city, and you could use this to try to do predictive models of cloud formation and how clouds are moving across a city. And then lastly, on the software side, we're asking a lot of questions, but one question is, can we bring something like cloud computing resources, which have experienced radical reductions in cost due to commercial cloud clusters like you have with Amazon and Google, can we bring this massively parallel architecture, which can be really cheap, and use that to improve numerical weather prediction models and machine learning, possibly just by brute force? I mean, when you think about these chaotic systems, the way to tackle it is often by doing a lot of scenarios in parallel and then getting some kind of probability distribution function. So this seems ideally suited to what the cloud could do. And then a last question we have to ask is, how can we complement, other Department of Energy projects, such as one going on with the National Oceanographic and Atmospheric Administration, NOAA. They have a project called the Wind Forecasting Improvement Project. So what they're doing is they're using kind of existing sensors and seeing how more or less data can help and improve forecasts. And so the question is, what can we learn from them, and what kind of sensing capabilities can we give to that effort, which is going to improve forecasting overall? So this is not a program and may never be, but if it were, we thought that a fun name for it would be Predicting Renewable Optimum Production of Heat and Electricity Technologies, or PROFIT.
Thank you, Phil. Good morning, everyone. My name is Tim Heidel. I'm an ARPA-E fellow here. Before joining ARPA-E, I did my PhD in electrical engineering at MIT, and more recently, I was the research director for MIT's Future of the Electric Grid study that was released in December. This morning, I'd like to talk to you about real-time electricity pricing. As we all know, demand varies over each hour of the day, over the days of the week, and the seasons of the year. And since we can't store electricity cost effectively at the bulk scale yet, we need to actually build generation capacity that's able to meet peak demand, even if that peak demand only occurs during a small number of hours each year. What this leads us to is this plot here. On the x-axis, I've plotted generation capacity installed, and on the y-axis is capacity factor. And if you look at this, you see that only 20% of generation is actually used less than 10% of the time. In fact, 40% of our generation is used less than 50% of the time. This is a recipe for high costs, because it means that we have to install all of our generation, and yet much of it only operates a small number of hours each year. And so we're very interested in ways, okay, how can we change this picture and flatten this curve? Well, there is an obvious answer, and that obvious answer is that the cost of generation actually varies already. And that as demand increases, the cost of providing that generation increases as well. And yet today, most consumers in the U.S. only see a flat price. They have no incentive whatsoever to shift their consumption off-peak into the valley areas. Now, we've had demand response programs that have been extremely successful in the last decade or two that have really shaved off the absolute peak of the peak. But in order to actually get more of the curve to flatten, we're going to have to pursue dynamic pricing in some way, shape, or form. Now, there have been a variety of estimates for what are the benefits of this. And every time we start to evaluate ARPA-E projects or programs, we really look at what is the impact. And one recent estimate gave us that dynamic pricing could lead to estimates and savings as much as $8 to $13 billion. So there's a huge prize here if we can figure out how to do dynamic pricing. Now, unfortunately, or just the fact of the matter is, dynamic pricing requires more granular measurements of electricity consumption. And today, the number one tool for enabling the more granular measurement of electricity consumption are smart meters. And unfortunately, today, they remain too expensive for many utilities throughout the U.S. And so the question is, how do we find the substantial cost reductions that are needed in order to enable dynamic pricing? Well, if we look at the way industry is doing it today, and this is a diagram from NIST that sort of tries to frame the customer interactions with the smart grid, just about every vision we've seen throughout industry relies on a smart meter at every single customer location. So every single customer gets some new meter that does the more granular consumption of electricity. And there have been a lot of efforts at reducing the cost of these meters and the associated communication systems, and there certainly are additional cost reductions that are possible here. But what we're asking at ARPA-E is there a fundamental learning curve we can move to? Are there ways, are there approaches that might be possible to enable ubiquitous dynamic pricing without replacing every single meter at every single consumer? Let me give you a couple ideas we have so far, but I'm very interested in hearing any additional ideas you might have for how this might be done. The first one is to move the measurement of electricity from the threshold of the customer into the individual appliances that actually use electricity, and especially those appliances that could be automated to actually shift their consumption without impacting the customer. So what we would need here is we would need cheap, secure, and accurate integrated power measurement devices. Now, there have been efforts in the last couple of years to design system-on-a-chip integrated circuits for doing this, but very few of those have yet achieved actually a revenue-grade accuracy that would be needed in order to be used in utility billing systems. And so this would be pushing the envelope in terms of both those chips that you're actually going to be integrating into the appliances, and then also the meter data management systems that actually integrate individual appliances from consumers instead of doing everything at the household level as we have traditionally done. The second way we might be able to do this is, instead of moving the measurement into the home, move it outside the home. There have been technology development efforts over the last several decades on a technology that is known as non-intrusive load monitoring, or you might have seen this as load disaggregation efforts. Most of these have been applied to the individual building or the individual residential area, and this is a very simple plot to show you how this works. You're looking at about 40 minutes of time on the x-axis here, and you're looking at power consumption on the y. And what you see here is that as you turn on and off each appliance within the home, there's a specific signature associated with each of those individual appliances. Now, this is just showing you magnitude here, but there have actually been a variety of efforts looking at very advanced and sophisticated statistical methods for how do you actually disaggregate each of these loads. Now, the vast majority of this has been done at the household level thus far, and the question we're asking is, could you back this up to the substation? Could you put very sophisticated measurement devices and computational power at a distribution substation and measure all of the homes on that individual feeder or on a couple feeders all at once and disaggregate those loads? Now, there's no question this would be a very, very hard problem. But I have not yet been able to find anybody who's been able to tell me why this is not possible. The idea for this, if it were to become a program, might be providing real-time intelligent costs for electricity or price.
Hi everyone, I'm Nick Cizek. I'm an ARPA-E fellow. I was an optical engineer at 2 startups and then did a PhD at Stanford in applied physics, where I studied ultra-cold atom physics. Today I'll be talking to you about cooling, but on a vastly different scale, namely power plants, and specifically how do we cool power plants using no or low water. The reason you might want to do this, you can see from this Sankey diagram of U.S. water flows. And I want to draw your attention to the circle here. The biggest user of water in the United States is power plants. And what happens is we take the water from surface water, whether it's oceans or lakes and streams, bring it into the power plant, and some of that water we evaporate, and some of that water we put back, but we put it back hot. The big issue with this is that this water that we put back hot is actually, there's new legislation from the Clean Water Act that is going to make this more difficult, and so it's going to get tricky for power providers. So the big question is, how are we going to produce this electricity if we don't have this water? The other thing is that the U.S. population is projected to grow 30% by 2030, and it's going to grow in places that are dry, that are already undergoing water scarcity. So California, Texas, Arizona, Florida. So the way we cool power plants today, I guess the bottom line is that we're going to need to make more power, and we're going to have to do it using less water. So the way we cool power plants today, there are 2 ways. One is closed-loop cooling, where you take water from some surface water, you run it in a closed loop between the steam condenser and a cooling tower, and essentially all of that heat goes into evaporating water. Let's see. The other is open-loop cooling. Open-loop cooling, you take the water from some body of water, you put it into the power plant, run it past the steam condenser one time, and then you put it back out to that body of water. And so the heat goes into raising the water temperature, which then raises the air temperature above it, and also adds to the evaporation rate of that water. And what you'd really like to do is just put the heat directly into the air with no water evaporation. So that's the problem statement here. how do we go about dissipating gigawatt scale low-grade heat into air without evaporating water? When I say low-grade, it's very low. It's like 95 Fahrenheit, 35 Celsius. So an air-cooled power plant is one way to do this. This has been around since the 1930s. What they do is take that cooling tower and replace it with a giant radiator, much like the one that's in your car. So the beauty of this is that the heat raises the air temperature only. You really get very little water evaporation. But for those of you who have been to one of these power plants, that is what the air-cooled condenser is. So it's as big as the power plant. It's expensive, and the big problem with it, though, is that the temperature on the cold side of your condenser is now the temperature of the air during the day, rather than the temperature of the water that you were cooling with. So if the temperature of that water, if it were in a river or a lake, is going to be the average temperature of the day and night. And so it's going to be colder than the air. And so what this leads to is a 5 to 15% loss in the amount of electricity you can produce with these power plants. So there are two big questions with power plant cooling that need to be addressed. One is, are there dry cooling technology pathways that will allow us to get that cold side temperature to be the average of day and night, like with water today, but using air as the cooling? And that would enable us to avoid this 10% efficiency loss. I think this is a very, very challenging problem. To do it, essentially you need something that's just like a lake, except you want a lake that doesn't evaporate. So maybe you could think about one big thermal body we could think about coupling to might be the Earth itself. Another, maybe you could think about having some kind of liquid other than water that's lower vapor pressure. However, if you don't figure out how to do this, you're going to be stuck with this efficiency hit. And so the question then is, if you're in a place that needs power but doesn't have water, how are you going to go about cooling the power plant? And how are you going to do it cost effectively? So the other part of this is, what technology pathways are there to achieve a wet cooling levelized cost of electricity? One way is to increase the surface area of your heat exchanger. There are new materials like metal foams, or people are actively working on trying to develop thermally conducting polymers, and if you could figure out how to make these cheaply, you could perhaps make larger surface area heat exchangers. Another is to increase the airspeed across your heat exchanger, and one way you might think about doing this is to elevate your condenser. If you could put that condenser up at windmill height, across a lot of the United States you have a 5 or 10 meter per second wind automatically that you wouldn't have to pay for. Another is to just directly go after the heat transfer coefficient of the heat exchanger, and this could be done perhaps through nanostructures or coatings or a surface finish. And then finally, maybe we need to consider non-ranking bottoming cycles. For example, Stirling engines are typically air-cooled, and maybe you could take a route like putting many of them in parallel. So I think it's pretty clear that the techno-economic goal of such a program needs to be that we can get dry-cooled power down to the same price per kilowatt hour as wet-cooled power. So 5 cents per kilowatt hour would be a good target for a dry-cooled power plant. And finally, if we were to run a program in this space, a name we might use would be Improving Cooling Efficiency of Power Plants, otherwise known as ICEPOP. Thank you very much. Oh, there you go.
Thanks, Nick. Good morning. My name is Asegun Henry. I am one of the ARPA-E fellows. I've been with ARPA-E for about a year. I did my PhD in mechanical engineering at MIT. I then went on to do 2 postdocs, one at Oak Ridge National Labs and the other at Northwestern. And in a couple months I'll be starting as a faculty member at Georgia Tech. What I want to talk today about, even though my background is in heat transfer, is potentially a new potential pathway to think about how to do high efficiency solar. So, we're very much aware of the existing learning curves, and we're very much proponent that those are successful potential ways to get to cost effectiveness. However, at ARPA-E we're always looking for potential new learning curves, and so we want to talk about a potential different pathway we can look at to push down a different learning curve that could potentially be cheaper and more efficient. So one of the ways I think about solar is that really it breaks into 2 processes. First, you have to collect the light, which comes to us pretty diffusely from the sun, about 1 kilowatt per square meter. And then secondly, we have to convert the light to electricity, right? And so what you need is you need the collection to be cheap, and then you need the conversion to be really, really efficient. And so in a sense, if you look at what's fundamentally out there, we have the makings of some things that we have something to start with. So we do have mirrors. Flat plate mirrors can be made very cheaply on the order of $10 per square meter. And then somehow we want to connect that with devices that are really efficient. And photovoltaics have the potential to be really efficient. I mean, here you have a plot, which you can't see the axes very well, but it's basically showing the external quantum efficiency of a single crystalline silicon cell. And you can see that over a broad part of the spectrum, you get more than 90% external quantum efficiency, which means that for those photons, you have a 90% chance that you can get them out as electrons. The problem is that you get those electrons out at a much lower voltage, which is close to the band gap. And so there's the potential for it to be high efficiency, but really what we're doing is throwing in broadband light into devices that give us all the energy out at a single voltage. And we'd like to somehow take advantage of having those photons come in and getting them out at high efficiency close to the band gap. So one of the things we tend to do is we try in flat plate PV to take the converter and make it really cheap. So we try to go to the left, and we try to take something that started out potentially really with high efficiency, and we sacrifice a lot of efficiency trying to make it really cheap. And so this is one learning curve. This is one direction we go. And again, the reason that this is problematic is because you have the whole spectrum there in the middle, and you get all of those photons out at a lower voltage. Another thing we think about in CPV is then to say, well, let's take the collector and let's just add it directly with a really good converter. And what we try to do is use multi-junction cells, which are much more expensive, but what we do is we concentrate the light, so we shrink their size, and so it actually makes it more affordable. And this is good. This is a good pathway forward, and this allows us to get it out at 3 different voltages in triple junction cells. But these cells get to 30 to 40% efficient, but there's still a big gap between that 40% and maybe the 90% external quantum efficiency. So how can we actually get closer to really taking advantage of the power and the potentially high efficiency of PV cells? And so one of the key things I want to point out here is that what we learned with CPV is that, and for flat plate PV, the actual module, the cell, is the majority of the cost. And so when you go to CPV, because you're concentrating on light, the cells are no longer the major cost, even though they're actually orders of magnitude more expensive than flat plate cells. And so what we're doing here is we learn this lesson that if we concentrate, we can actually add complexity and get to higher efficiency. So we've done that once, but what about doing it again? Can we actually go one more step? Can we actually concentrate further and afford to introduce additional complexity? So for triple junction cells, you have a difficulty in adding more band gaps because you have to be lattice and currents matched between the different layers. But what about going to many more band gaps? How can we get to like 10 or 20 band gaps? So that's what we'd like to do to be able to get solar cells to this high efficiency. And so what we can think about doing is, what if we actually add a new layer of complexity? Let's add an optical system that, in a sense, preconditions the light so that we're feeding into each solar cell the optimal photons that are actually going to be converted at the highest efficiency. And so we can actually think about, we have to raise the concentration again to keep these components cheap enough to the system cost. All right, so what would this look like? Let me give you one particular picture of what this might look like. There are probably a wide variety of ways that you can imagine engineering this optical system that preconditions the light. So what about doing power tower CPV, right? What if we take advantage of cheap collecting optics, and then we focus the light up to a power tower, but imagine in the power tower we have another device now that actually manages the light. So if you imagine having this kind of cone structure where the light enters and gets concentrated even further up into this cavity where then it expands onto a spherical cavity that's lined with different types of solar cells. Each one having a filter on top of it that's just a bandpass filter and only allows the light that will be converted efficiently in that triple junction or many junction cell below it to pass through, and reflects everything else and keeps the light bouncing around until it finds a cell that it can be converted in efficiently. Something like this would, allow you to potentially convert at higher efficiency, and also would give you very even illumination on the different cells. And so you wouldn't have these kind of trade-offs that you have typically with when you're concentrating light, and you have this trade-off with having to have very accurate tracking. So we're thinking that a goal for going in this direction would be to push way beyond typical solar efficiencies and try to get to above 60% efficiency and below $1 a watt to show that this is a potential pathway to be disruptive to our current learning curves in photovoltaics. So one question that usually comes up when you start talking about higher concentrations, people always say, well, can you handle all that heat? That's a lot of heat. And so I just throw up this basic example. You can imagine if you had a triple junction cell that was only 20% efficient, at 1000x, you'd have 20 watts per square centimeter of electricity coming out and 80 watts per square centimeter of heat to deal with. But if you look on the left, this is a plot of heat dissipation in different electronic devices. You can see that 80 watt per square meter, this 80 watt per square centimeter heat dissipation load actually falls within a regime that we can handle with water cooling heat sinks. And so that's not an intractable problem, doing the cooling. And so now if we're talking about adding optics that's working at even higher concentration, how would that work out? Right? So the thing with the optics is that what you would want to do is you would want to concentrate the light so much that you can use the highest performance optics possible. And so you can imagine having optics that have less than 1% absorption. And so if you're at 10,000x with 1% absorption, now you've only got 10 watts per square centimeter of heat load to deal with. Now, you can imagine having some optical components that you're not able to remove the heat off the back, so maybe you have to actually conduct the heat out to the sides, and that could be a big problem. Right? So maybe we can think outside the box, and maybe you can actually integrate the cooling strategy into the design of the optics itself. So optical high-performance optics usually have many layers of dielectric material. What if one of those layers was a liquid, and you're actually flowing it and removing the heat actively as you're using it? So we think there may be some white space here in two different areas to think about spectral splitting, but at really, really high concentrations so that it becomes affordable and doesn't add a major cost to the system. And that allows you to possibly get to higher efficiency. And then also thinking about how do you redesign optical components so that their heat management strategy is already integrated into their design. So we're not sure if there will ever be a program in something like this, but if there was, we think a cool name might be photovoltaics, highly optimized through optical networks, or photon.
All right, well, let's give the fellows a hand. So now I want to invite you to write down your questions or comments to the fellows on their program ideas and pass them into the middle. In addition to that, this is a really great chance, and probably one of your best chances to stand up, to either send us, write down a program idea that you think we should consider that we haven't been looking at yet, or do that at the microphone as well. So now I'd like to open up the floor for your thoughts, feedback on these ideas, and also for you to stand up and tell us areas that you think we should work. Sir.
Good morning, Guy Lay with Intel Labs, and I'm going to take a very out there position on real-time pricing and suggest that that's a gross misallocation of resources compared to distributed electrical storage, which would completely obviate the need for real-time pricing and also mitigate most of your cybersecurity issues.
Is this on? Thank you. There's no question that storage is also another alternative, and I think that there are a lot of people working very hard on storage, and there are a lot of people working very hard on real-time pricing.
Well, yeah, and I guess I need to be specific. It's really needs to be a national priority for low-cost distributed storage. Thank you.
Thank you. In the middle.
My name is Shane Sabrick. For similar question to the gentleman from Intel. Real-time pricing involves the human element, and you got to get the human element out. And smart metering with the pricing you mentioned, the gentleman, electrical engineer from MIT. I'm sorry, I don't know your name.
Tim Heidel.
Hi, Tim. I suggest to you that, for example, we have a patent pending project at my company that is working on extremely distributed, very low data rate, energy harvesting sensors that use the machine-to-machine network and does the cloud computing using neural nets to distribute the information at the point of load, not at the meter. So take the human element out, use your predictive modeling and take the information at low data rate from the machines using the next machine-to-machine internet.
Couldn't agree more. I think automation in end uses is an absolutely critical problem.
Here on the left.
Yeah, Richard Wurs from UCLA. And one thing, I like the ideas of trying to look at these emerging technologies that could make a big impact. But the thing I'm not seeing, and I think is generally a problem in our community, and something that ARPA-E should fix, being a more advanced institution, is the idea that it's not about, hey, look, we're going to save $1 billion. What does that mean? That doesn't mean anything. Because the problem is not, do we need to save $1 billion here and there? This is a terawatt hour type problem. And if we don't take what we're doing and say this is going to have this percentage of impact on our infrastructure, and let's say just in our nation, or you could use percentage, that would be something people could relate to, or this is going to have some terawatt hour level impact. I think that's going to actually say, are we getting to a solution? Because if we save, let's say, $50 billion, well, what does that mean? Does that mean that we're solving 5% of the problem, or we're really getting at 50% of the problem? So I just like to see that when you're talking about these emerging ideas, what can they actually do? So that would just be something I'd like, as we move forward, I'd like to see that happen more. Something where we have more constructive metrics that we can use to see what our impact actually is.
Well, thanks for your comment. I think if you saw this morning, the first and foremost criteria in ARPA-E's mind is impact. Exactly what you're bringing up. So we're 100% in sync with you on that issue.
Okay, thank you.
In the middle?
Yeah, I had a question about the real-time electricity pricing. I'm a real proponent of open, transparent markets. I think that drives the behavior we want. I was just curious if you knew of any political difficulties in implementing that. If it's a flat pricing now, then someone is being subsidized, and that's the user, the residential user who's home during peak times during the day, which is probably a stay-at-home parent or the elderly. And so from a political point of view, if those people are going to be paying more on a real-time pricing, is there pushback, given that that would probably be the people who would pay more? Do you know of anything like that?
I have seen a couple studies on the distributional effects of real-time pricing. I don't remember off the top of my head, the magnitudes of different changes. Quantifying the benefits and quantifying the different benefit streams associated with the enabling technology that allows you to enable dynamic pricing has always been a very contentious and difficult issue. And so one of the questions we're asking here is, can we just simply remove that off the table and make this technology just so cost effective that you simply cannot not implement it? But there's no question that there are also other social issues that are very difficult and will have to be overcome.
Hi, Don Paul with the University of Southern California. Just following up again on real-time pricing, I know in our smart grid work, one of the components is understanding the human and social behavioral aspects. And one of the problems that I think we have with real-time pricing is that people would really like flat, low costs. And so one of the questions that I think comes up in general in a lot of these areas, that in an information-rich world, as technology touches consumers begin to organize an opposition. As we've seen with smart meters, they begin to say, I'm going to pay more, but who benefits? The utility? So this is the other issue. Who benefits from all the savings that you're going to get? And how do you engage consumers to understand that real-time pricing may not be their enemy?
Yep, we have one program that ARPA-E has already funded that's looking at a lot of those social issues related with pricing and demand response, and I think there's a lot more work to be done there.
Hi, my name is Adam Rosenberg. Hey, Dave. I work for the Department of Defense, and this question is for Mr. Henry. We're currently very interested in taking a serious look at high-efficiency solar, particularly to enhance mobility for small combat units, and any amount of energy that we can use to reduce the need to transport and force protect fuel convoys is a big win for us. I'm curious if you have looked into the potential mobility of the system that you're proposing.
I haven't thought so much about mobility. Is this on? Yeah, I haven't thought so much about mobility, but that is a very interesting aspect to consider for sure.
We'd be very interested in talking with you.
Yeah, I'd like to follow up with you later.
Thanks.
So I'm going to take one of the note card questions again for Asegun. You put forward one idea for a very highly efficient approach to solar conversion, but there's a comment here about there are other kind of third generation beyond solar concepts that could have much higher efficiency than we have today. Is that something that you think would fit within a program idea like that or not?
It depends, I guess, on which idea it is, but I think that the way I look at it is that a lot of the funding in this area has gone towards improving cell efficiency itself. And if you're going to concentrate, the majority of the cost actually comes down to how do you get the light into the cells in the first place. And so, I'm thinking that where the new learning curve might be is in how do we actually do that cost effectively, or reduce the cost of that component, because the cells, pushing the cell efficiency further is more so on an existing learning curve. And but to the extent that there are breakthrough ideas, maybe multi-exciton ideas and things like that, I think those are other possible breakthrough approaches.
In the middle.
Hi, my name is Ed Pyle. I wanted to comment on the low and no water power plant cooling. Two thoughts on that. One is if you can put the power plant in tandem with a current operating mine and using the mine to run the air through on the outlet to heat the mine, for the miners supply air and to ventilate the mine and stuff, there might be some potential. It's probably limited to the number of mines and the surface area that you would have for that. So just a thought. The other part on that one is one of the ways to get the heating exchange system down is to actually increase the temperature at which you reject the heat at. This is exactly the same issue that NASA works on constantly, because they can only radiate heat out to space. You have a much smaller problem than they do, because you have to radiate at very high temperatures. But on the Earth, with the air cooling and stuff, if you raise the temperature with the reject heat a bit, then the system gets much smaller in size without having to try to raise it up in height or something like that.
Nick, do you want to address that question?
Yeah, Ed, thanks for the question. So I think the idea about the power plants in tandem with mines, just in general, there are things that maybe we could use this air or this heat for, and if we can couple those together, that would be great. I think we all agree that would be a terrific win for the whole system. In terms of the heat exchanger, increasing the temperature, I guess I was under the impression that you needed to get that temperature low because you want to keep the back pressure on the turbine low so that you can extract more of the workout. But I'd be happy to follow up with you after the presentation to talk about it more.
Here on the left, please.
Thank you. It's Don Baker, Science Commercialization Ventures. I'm not sure how artfully I can ask this question, but can you explain from a macro point of view how you will go about evaluating comparing something that would be truly disruptive but only deployable, say, in 10 years versus something that would be more incremental in your subject matter that could be deployable much more rapidly than that? How you go about making a decision internally about which to support or allocation of resources.
I mean, I'd make a comment is that, I was at first program director at ARPA-E, so thinking hard about those kind of questions. And, one thing we talk about, we're all about high risk, high reward. We'll take low risk, low reward, but you don't find a lot of those things sitting around, and you don't find a lot of those to be areas that have been seriously underinvested in. And so the other parts of DOE and the applied programs, such as the Energy Efficiency and Renewable Energy Program, are working on problems that are on existing learning curves with very high impact where we can make a difference, But ARPA-E is going to be all about those new learning curves and the white space. In the middle?
Yeah, Dominic Lee, Oak Ridge. This question concerns the weather forecasting for renewables. Obviously, when and if the storage challenge gets solved, the impact of forecasting will diminish. So do you see this forecasting challenge as being shorter term, easier to achieve than storage?
I'm a large fan of electricity storage. One of the things you'll hear often enough is if we had electricity storage that was cheap and efficient, then we could solve almost all problems with renewable energy integration. So yes, that would obviate the need for a lot of the electricity forecasting from wind and solar power. However, it might not eliminate it, and here's one reason why. Let's say that your storage efficiency is 70%, 50%, who knows? If you look at compressed air energy storage, other means of electricity storage, sometimes you want to trade off efficiency for capital cost. So let's say that you had a bunch of reasonably cheap, ubiquitous, but really not that efficient electricity storage. Well, then, the optimal thing is still to dispatch your wind directly into consumers. So I guess what I would say is even if there's electricity storage, but the efficiency isn't that high, you would still want to know what the wind power production is to be able to schedule it optimally so you didn't have to take a 30 or 50% efficiency hit.
But I thought the attribute of being able to schedule your renewable is to be able to use excess generation, which is typically much more expensive for load leveling.
Well, it's not only about using excess production. It's also kind of a reliability issue. So if you're scared the wind is going to underproduce, then you have to have other resources standing by, whether they be storage or gas generation or whatever. So I'm just saying, the optimal algorithm isn't necessarily to just dump whatever wind you have into the storage. It might be the case that you need to know what the wind output is going to be to dispatch optimally, depending on what all the variables in the system are. But it's an excellent point. As with many things, and was raised before with real-time pricing, cheap electricity storage would be a big game changer, and we have a lot of projects looking into electricity storage for that reason.
Well, great. With that, I think we'll bring the panel to a close. We have a lot of good questions here. We'll make sure that they get to the fellows, and at least for the next few minutes, the fellows will be here up front available to talk to you one-on-one. We have about 10 minutes until lunch starts, and why don't we give the fellows one last hand of applause.